Hello there, and welcome to Simple Sleepy Science. Have you ever wondered why the most destructive forces in nature can also be the most beautiful? Why storms that could flatten cities are given gentle human names? Tonight, as you settle into sleep, let's explore the peaceful science behind one of Earth's most misunderstood phenomena: the typhoon, a force that's not chaos, but order, not destruction, but balance, not random, but rhythmic as a heartbeat. Before we begin this journey, please take a moment to like and subscribe so you don't miss more amazing stories tomorrow. Leave a comment telling us where you're watching from and what time it is there. We love hearing from you. Now, let's talk about something that confuses many people. The word typhoon itself carries mystery. You've heard of hurricanes, you've heard of cyclones. You've probably wondered if they're different storms or just different names for the same thing. The answer is both simpler and more beautiful than you might imagine. A typhoon is essentially the same phenomenon as a hurricane. The wind speeds, the spiral structure, the eye at the center, all identical. What changes is not the storm itself, but where it forms on our planet. Think of it like this. Water is water, whether you call it agua, o, or magi. The substance doesn't change, only the language we use to describe it. Typhoons are hurricanes that form in the Northwest Pacific Ocean. That's the only difference. Same storm, different address. Here's how the naming works. If a tropical cyclone forms in the Atlantic Ocean or the Northeast Pacific, we call it a hurricane. If it forms in the Northwest Pacific, specifically west of the international dateline, it becomes a typhoon. If it forms in the South Pacific or Indian Ocean, it's called a cyclone. 3 names, 1 phenomenon. The storm doesn't know what we call it. It simply spins according to the laws of physics, indifferent to human labels. This geographical distinction isn't arbitrary. It reflects how different cultures and meteorological organizations developed their own terminology over centuries. Asian nations along the Pacific Rim used the word typhoon, likely derived from the Chinese word taifeng, meaning great wind, or possibly from the Greek typhon, meaning whirlwind. Western nations monitoring Atlantic storms used hurricane, from the Caribbean Taino word huracan. Each region named the same natural process based on their own linguistic heritage. What matters isn't the name. What matters is understanding that these are all rotating storm systems born from the same recipe. Warm ocean water, humid air, and the subtle spin of Earth's rotation. Whether you're in Manila watching a typhoon approach, in Miami tracking a hurricane, or in Madagascar monitoring a cyclone, you're witnessing the same atmospheric machinery at work, the same physics, the same beauty, the same power. This realization brings a strange comfort. Nature doesn't have different rules for different oceans. The patterns are universal. A typhoon follows the same principles as every other tropical cyclone on Earth. Understanding this universality helps us see these storms, not as chaotic monsters, but as predictable expressions of atmospheric thermodynamics. They're part of Earth's system, as natural as rain, as regular as tides. So, tonight, as you close your eyes, remember that knowledge brings clarity. What seems like 3 different storms is actually one phenomenon wearing 3 different name. And that phenomenon, as we'll discover, is far more organized and purposeful than you ever imagined. But what actually creates these spinning giants in the first place? The birth of a typhoon is surprisingly gentle. There's no sudden explosion, no dramatic moment when a storm springs into existence. Instead, it begins with something as simple as sunlight touching water. Imagine the tropical ocean on a calm day. The sun has been heating the surface for weeks, warming it to at least 80 degrees Fahrenheit. This temperature isn't random. It's the precise threshold where water molecules gain enough energy to escape the ocean's surface in large quantities. Below this temperature, evaporation happens too slowly. Above it, the ocean becomes a factory for storm fuel. Water molecules rise invisibly into the air, carrying with them something precious. Energy. Not the energy of motion or sound, but thermal energy absorbed from sunlight over days or weeks. Each molecule is a tiny battery, storing heat that will later power winds and rain. This process happens constantly in tropical regions. Most of the time, it creates nothing more than clouds and brief showers. But occasionally, conditions align. The rising water vapor cools as it climbs higher into the atmosphere. Eventually, it condenses back into liquid droplets, forming clouds. This transformation releases the stored heat energy. The air around these forming clouds warms up. Warm air is lighter than cool air, so it rises further, creating an upward current. More air rushes in at the surface to replace what's rising. More water evaporates. More clouds form. More heat releases. The cycle strengthens itself. This is the engine of a typhoon. Not fire or fuel, but the simple phase change of water from liquid to gas and back to liquid again. The ocean is the gas tank, the sun is the charging station, and the atmosphere is the engine where energy converts into motion. But here's what makes this process beautiful rather than terrifying. It's slow. A typhoon doesn't appear in an hour. The initial disturbance, what meteorologists call a tropical disturbance, might persist for days without organizing. It's just a cluster of thunderstorms, unorganized and weak. Slowly, if conditions remain favorable, the system begins to show structure. The thunderstorms arrange themselves in loose spirals. A center starts to form. At this stage, it becomes a tropical depression. The winds are still gentle, less than 39 miles per hour. The system now has a defined center of circulation, but it's fragile. Wind shear, which is the change in wind speed or direction with altitude, can tear it apart. Dry air can choke it. Cooler water can starve it. Many tropical depressions never become anything more. But if the system survives, if the ocean remains warm and the atmospheric conditions stay favorable, it strengthens into a tropical storm. Winds reach 40 to 73 miles per hour. The spiral structure becomes more obvious. This is when the system receives a name from the official list. It's no longer just a numbered disturbance. It's being tracked carefully now. Throughout this entire process, from the first water molecule evaporating to the organized tropical storm, days or even weeks have passed. Nature isn't rushing. Every step follows physical laws as reliable as gravity. The storm builds layer by layer, cloud by cloud, using only sunshine and seawater. There's something deeply calming about understanding this patience. Typhoons don't ambush. They announce themselves slowly, developing over vast stretches of ocean where satellites watch their every move. This gradual formation gives us time. Time to prepare, time to watch, time to understand what's coming. This spinning has a name, and understanding it reveals something profound about our planet. The Coriolis effect sounds complicated, but it's actually one of the most elegant pieces of physics governing our planet. It's the reason typhoons spin, and understanding it transforms these storms from frightening chaos into mathematical precision. Here's the key insight. Earth rotates, not just day turning to night, but actually spinning at over 1,000 miles per hour at the equator. You don't feel this motion because you're rotating with it, like a passenger on a smoothly moving train. But this rotation creates an invisible force that affects anything moving across Earth's surface, including air. Imagine standing at the North Pole and throwing a ball toward the equator. You'd aim straight south, but while that ball travels through the air, Earth beneath it continues rotating eastward. From your perspective at the pole, the ball appears to curve to the right. It's still traveling in a straight line through space, but relative to the spinning Earth below, its path curves. This is the Coriolis effect. The same principle applies to air rushing toward the low-pressure center of a developing typhoon. Air flows inward from all directions, trying to fill the low-pressure area. But as it moves, Earth rotates beneath it. In the northern hemisphere, this rotation makes the incoming air appear to curve to the right. In the southern hemisphere, it curves to the left. Picture water spiraling down a drain, except the drain is hundreds of miles wide, and the water is air. In the northern hemisphere, where most typhoons form, this rightward deflection creates counterclockwise rotation. Every air current moving toward the center gets deflected slightly to the right, creating that characteristic spin we see in satellite images. South of the equator, the leftward deflection creates clockwise rotation. The equator itself is unique. Right at 0 degrees latitude, the Coriolis effect is 0. There's no deflection. This is why typhoons never form directly on the equator. They need that rotational nudge to organize their spiral structure. Typically, typhoons form at least 5 degrees north or south of the equator, where the Coriolis effect becomes strong enough to generate spin. Think of Earth as a massive carousel. If you're standing at the center, you barely turn. But if you're standing at the outer edge, you're moving much faster, completing the same rotation in the same time, but covering more distance. The Coriolis effect works similarly. It's weakest at the equator and strongest at the poles, because the rotational impact on moving objects increases with latitude. This isn't random violence, it's geometry. It's the natural consequence of motion on a rotating sphere. Every typhoon that's ever formed has spun according to this same principle. Every hurricane, every cyclone, all following the same law. The predictability is actually comforting. Meteorologists can look at a developing storm and know instantly which way it will spin based purely on its latitude. Northern Hemisphere, counterclockwise. Southern Hemisphere, clockwise. No exceptions. This reliability extends to the storm's structure, its movement patterns, and its behavior. The Coriolis effect doesn't just make typhoons spin, it makes them spin consistently. As you rest tonight, consider this. The same force that makes typhoons spiral also affects ocean currents, aircraft flight paths, and even artillery shells. It's woven into the fabric of any motion on our rotating planet. The universe has rules, and those rules create patterns we can understand and predict. At the very center of all this motion lies something unexpected. The eye of a typhoon is one of nature's most counterintuitive creations. Imagine standing in winds that could peel bark from trees, rain so heavy you can't see 5 feet ahead, and then suddenly, complete calm. Blue sky appears overhead. The wind drops to a gentle breeze. The ocean, though still churning from recent chaos, begins to settle. You're inside the eye. This cylinder of tranquility typically measures 20 to 40 miles across, though some eyes span 60 miles or more, while others compress to just 10 miles wide. The size varies, but the principle remains constant. The eye is not an accident of storm formation. It's a requirement, a necessary consequence of how rotating air behaves at extreme speeds. Here's why it forms. As air spirals inward toward the low pressure center, the Coriolis effect and the conservation of angular momentum cause it to spin faster and faster. Think of an ice skater pulling their arms inward during a spin. The air accelerates as it approaches the center, creating the eye wall, which is the ring of most intense winds and heaviest rainfall surrounding the eye. But air can only spin so fast before physics intervenes. At the very center, the centrifugal force becomes so strong that air actually can't reach the middle anymore. It's flung outward by its own rotation. This creates a hollow core, a void that needs filling. The only direction air can come from is above. So air from the upper atmosphere descends into the eye, warming as it compresses under increasing pressure. This descending air is dry and stable. It suppresses cloud formation, which is why the eye often has clear skies. The warming also evaporates existing clouds. Meanwhile, the descending motion creates a downdraft that opposes the updrafts trying to form. Everything about the eye's structure works against the turbulence happening just outside its walls. People who've experienced the eye passage describe an eerie serenity. After hours of relentless battering, the sudden silence feels almost unreal. Birds sometimes appear, having been trapped in the eye as the storm formed around them, unable to escape through the violent eye wall. The temperature inside the eye is often noticeably warmer than the surrounding storm, sometimes by 10 to 15 degrees Fahrenheit, thanks to that descending, compressing air. The eye reveals something profound about balance. The faster the winds spin in the eye wall, the calmer the eye becomes. Intensity and tranquility aren't opposites here. They're partners, each depending on the other. A strong typhoon must have a well-defined eye. A weak tropical storm might not develop one at all. The eye is a sign of organization, of a storm that has matured into its full structure. Meteorologists use the eye to measure storm intensity. A smaller, more defined eye typically indicates a stronger typhoon. The pressure at the center of the eye, measured in millibars, tells us how powerful the storm has become. The lower the pressure, the stronger the surrounding winds. Some typhoons have recorded central pressures below 900 millibars. Compared to normal atmospheric pressure of about 10-13 millibars. This structure, violence surrounding perfect calm, exists nowhere else in nature quite like this. It's a reminder that extremes can coexist within the same system, that nature creates pockets of peace even within its most energetic expressions. The eye isn't fighting the storm. It's part of the storm, essential to its existence. But the eye isn't the only peaceful structure within these storms. From space, a mature typhoon looks like a work of art. The spiral structure isn't chaotic swirling. It's organized into distinct features, each one serving a specific function in the storm's machinery. Understanding this architecture transforms our perception from seeing random violence to recognizing deliberate design. The eye wall we've discussed forms the innermost ring, a circular fortress of the most intense weather, but extending outward from the eye wall are spiral rain bands, curved lines of clouds and precipitation that wrap around the center like arms reaching outward. These aren't decorative, they're conveyor belts, feeding moisture and energy into the storm's core. Each rain band is essentially a smaller weather system within the larger typhoon. As you move through a rain band, you'd experience heavy rain and gusty winds that intensify, then weaken as you pass from one edge to the other. Between rain bands, conditions improve significantly. The rain might stop completely. Winds calm, then the next band arrives, and conditions deteriorate again. This cycling effect means that typhoons don't produce uniform conditions. They pulse. The spiral shape of these bands comes from the same Coriolis effect that creates the storm's overall rotation. Air flowing inward curves, creating these elegant arcs rather than straight lines. The spacing between bands follows patterns meteorologists can predict. Typically, major rain bands occur every 30 to 60 miles, though this varies with storm size and intensity. Above the entire system, at altitudes of 30,000 to 50,000 feet, thin cirrus clouds stream outward in all directions. These high-altitude ice crystals get caught in upper-level winds and spread out like silk scarves, sometimes extending hundreds of miles from the storm center. These outflow clouds are crucial. They're evidence that the storm is breathing, exhaling air at high altitudes that it inhales at the surface. Without this outflow, the storm would choke on its own circulation. The structure has vertical layers too. At the surface, air spirals inward. In the mid-levels, around 10,000 to 20,000 feet, the heaviest precipitation forms. At the top, air flows outward. This three-dimensional organization means a typhoon isn't just a flat spiral. It's a cylinder, sometimes 10 miles tall, with different atmospheric processes happening at each level. Scientists have discovered that stronger typhoons tend to have more symmetric structures. Their rain bands space evenly around the center. Their eyes become more circular. Weaker storms show asymmetry, with rain bands concentrated on one side, often the side with better inflow conditions. This asymmetry actually prevents strengthening because it disrupts the efficient circulation pattern the storm needs. The most fascinating aspect is how self-maintaining this structure becomes. The eye wall creates the low pressure that drives inflow. The inflow feeds moisture into the rain bands. The rain bands transport energy toward the eye wall. The eye wall converts that energy into winds that maintain the low pressure. It's a closed loop, a self-reinforcing system that can persist for weeks if conditions allow. Temperature differences also show organization. The eye is warmest, the eye wall slightly cooler, the outer rain bands cooler still. This temperature gradient drives circulation just as temperature differences between poles and equator drive global wind patterns. The Typhoon is a miniature atmospheric engine running on temperature differential and moisture. Looking at satellite imagery, these patterns become meditation. The mathematical precision, the fractal-like repetition of spirals within spirals, the symmetry that emerges from fluid dynamics. This isn't disorder. It's one of nature's most organized structures, following rules as strict as crystal formation. This organization follows rules as reliable as gravity. Scientists created a system to measure typhoon intensity, not to frighten us, but to help us understand what we're dealing with. The Saffir-Simpson scale divides tropical cyclones into 5 categories based on sustained wind speed. It's a tool for clarity, turning abstract danger into concrete numbers we can prepare for. Category 1 begins at 74 miles per hour, the exact threshold where a tropical storm becomes a typhoon or hurricane. These winds can damage roofs, siding, and gutters. Tree branches snap. Power outages are common, but usually brief. Category 1 storms are the most frequent, accounting for about 40% of all typhoons that make landfall. They're serious weather events, but manageable with proper preparation. Category 2 ranges from 96 to 110 miles per hour. Now we're seeing more substantial damage. Shallow-rooted trees topple completely. Windows can break from flying debris. Power outages extend to days rather than hours. The storm surge, which is the rise in ocean water level caused by the storm's winds, reaches 6 to 8 feet. About 25% of landfalling typhoons reach Category 2. Category 3 marks the beginning of what meteorologists call major typhoons. Winds hit 111 to 129 miles per hour. Well-built homes sustain major roof and siding damage. Many trees snap or uproot. Electricity and water can be unavailable for weeks. Storm surge reaches 9 to 12 feet. This is where the exponential nature of wind damage becomes clear. A Category 3 doesn't cause twice the damage of a Category 1. It causes perhaps 10 times the damage. Category 4 storms are devastating. Winds range from 130 to 156 miles per hour. Most trees snap or uproot. Power poles come down. Houses lose most of their roof structure. Storm surge reaches 13 to 18 feet. Areas become uninhabitable for weeks or months. Only about 6% of typhoons reach this intensity, but they account for disproportionate damage. Category 5 represents nature's maximum output. Sustained winds exceed 157 miles per hour. Some Category 5 typhoons have recorded winds above 190 miles per hour. Complete roof failure is common on houses. Storm surge exceeds 18 feet. The damage is catastrophic and widespread. Fewer than 2% of typhoons reach Category 5, but they're the ones that get remembered for decades. The scale correlates directly with central pressure. Category 1 storms typically have central pressures of 980 to 990 millibars. Category 5 storms can drop below 500 millibars. This relationship isn't coincidental. Lower pressure means a steeper pressure gradient between the eye and the outer storm, which translates to stronger winds. Pressure and wind speed are tied together by physics. What's remarkable about this scale is its predictability. Once meteorologists measure wind speed and pressure, they know what category they're dealing with. There's no guesswork. The categories don't shift based on location or time of year. A Category 3 in the Pacific is identical in intensity to a Category 3 in the Atlantic. The scale provides universal language for discussing storm strength. Understanding these categories helps us recognize that not all typhoons are created equal. Most remain Category 1 or 2. The monsters we hear about in history books are rare exceptions, statistical outliers that occur maybe once or twice per decade in any given ocean basin. This knowledge allows appropriate response rather than panic. These categories emerge from one simple element. Water is the fuel that powers every typhoon, not gasoline or coal or nuclear reactions, but simple H2O, changing from liquid to gas and back again. This transformation releases more energy than most people realize. A single large typhoon releases energy equivalent to about 10,000 nuclear bombs. But unlike an explosion, this energy spreads across days and thousands of square miles, making it less a detonation and more a sustained burn. The process begins with evaporation. When liquid water absorbs heat energy from the sun, its molecules vibrate faster until some escape the liquid surface and become water vapor. This requires energy, about 540 calories per gram of water. That energy doesn't disappear. It gets stored within the water vapor molecules as latent heat, hidden energy that waits for the right moment to release. When that water vapor rises into cooler air and condenses back into liquid droplets, forming clouds, the latent heat releases. The air around those forming droplets warms up. This warming makes the air even more buoyant, causing it to rise faster, which creates lower pressure at the surface, which pulls in more moist air, which evaporates more water, which rises and condenses, which releases more heat. The cycle feeds itself. Think about steam from a boiling kettle. That steam carries tremendous heat energy. If you let it condense on a cool surface, that surface warms up as the water vapor gives back the energy it absorbed during boiling. A typhoon works on the same principle, just scaled up to atmospheric dimensions. The ocean is the kettle, the tropical sun is the stove, and the atmosphere is where the steam condenses and releases its energy. A single day of sunshine over tropical ocean water can evaporate about 1/4 inch of water depth. That might not sound like much, but spread over hundreds of thousands of square miles, it represents an enormous amount of water vapor entering the atmosphere. Most of this moisture falls back as regular rain, but in areas where atmospheric conditions allow organization, it becomes typhoon fuel. The efficiency of this energy conversion is remarkable. About 3% of the latent heat released in a typhoon converts into the kinetic energy of wind. The rest warms the atmosphere. Even that 3% efficiency, when you're dealing with such massive amounts of water vapor, produces winds exceeding 150 miles per hour in the strongest storms. If typhoons were more efficient, they'd be even more powerful. But fortunately, physics limits how much of that thermal energy can become motion. This is why typhoons weaken over land or cooler water. Cut off the fuel supply, the evaporating water, and the engine sputters. The storm can't maintain its intensity without constant replenishment of water vapor. It's like a car running out of gas. The engine doesn't explode, it just gradually slows down and stops. Scientists have calculated that the atmosphere over tropical oceans holds enough moisture to sustain multiple typhoons simultaneously. The ocean provides essentially unlimited fuel as long as temperatures stay warm enough. This is why typhoon basins can have several active storms at once, each one tapping into the vast reservoir of heat energy stored in tropical seawater. The elegance of this system lies in its simplicity. No complex chemistry, no rare elements, just water changing state, following thermodynamic laws as old as the universe. The most powerful storms on Earth run on the same physics that creates morning dew. But there's a temperature threshold that matters more than you'd think. The magic number is 80 degrees Fahrenheit, or 26.5 degrees Celsius. Below this sea surface temperature, typhoons cannot form. Above it, they become possible. This isn't an approximation or a rough guideline. It's a hard threshold established by physics, and understanding why reveals something fundamental about how energy flows in our atmosphere. At 80 degrees, water evaporates fast enough to supply the massive amounts of moisture a developing typhoon needs. The evaporation rate increases exponentially with temperature. Water at 79 degrees evaporates significantly slower than water at 80 degrees. That 1 degree difference determines whether enough latent heat energy can rise into the atmosphere to sustain organized convection. But temperature alone isn't enough. The warm water must extend deep, at least 150 feet below the surface. This depth requirement exists because typhoon winds churn the ocean, mixing surface water with cooler water from below. If only a thin layer is warm, this mixing rapidly cools the surface, cutting off the fuel supply. Deep warm water acts as a reservoir, maintaining high temperatures even as the storm stirs the upper ocean. This explains why typhoons form almost exclusively in late summer and early fall. The sun needs months to heat not just the surface, but the entire upper layer of the ocean. By August and September in the northern hemisphere, tropical oceans have absorbed 6 months of intense sunlight. The heat has penetrated deep. Now conditions are right. It also explains why typhoons weaken rapidly when they move over cooler water. As soon as sea surface temperatures drop below 80 degrees, the evaporation rate falls. Less water vapor means less latent heat release. Less latent heat means weaker updrafts. Weaker updrafts mean the low pressure center fills in. The storm loses its intensity gradient and winds decrease. Some typhoons lose category 4 or 5 intensity within hours of crossing into cooler water. The Pacific Ocean maintains vast areas of water above 80 degrees year-round near the equator. This is why the Western Pacific produces more typhoons than any other region on Earth. The warm pool of water there, often exceeding 85 degrees, provides optimal conditions for storm development. Meanwhile, the Atlantic has a smaller area of sufficiently warm water, producing fewer hurricanes on average. Climate scientists watch this 80-degree threshold carefully because ocean temperatures are gradually rising. Water that used to stay below 80 degrees now exceeds it during summer months. This expands the geographic area where typhoons can form and potentially lengthens the season. It's not that individual storms become stronger simply because water is warmer. It's that more areas of ocean become capable of supporting storm development. Interestingly, there's also an upper limit. Water above 88 degrees can actually inhibit typhoon formation in some cases because it creates very stable atmospheric conditions. The relationship between ocean temperature and storm development isn't linear. There's a sweet spot, typically between 80 and 86 degrees, where conditions optimize for rapid storm development. Meteorologists monitor sea surface temperatures constantly using satellites and buoys. When they see temperatures climbing above 80 degrees, they increase their vigilance. When temperatures fall below 80, they can relax slightly, knowing formation becomes unlikely. This temperature acts as a switch, turning typhoon season on and off with reliable precision. This temperature requirement creates a natural rhythm. Typhoon season follows Earth's rhythm with clockwork precision. In the Western Pacific, the peak months are August, September, and October. This isn't random variation year to year. It's a direct response to the sun's seasonal heating of the ocean, as predictable as flowers blooming in spring or leaves falling in autumn. The season begins tentatively in May or June. Ocean temperatures have just crossed the 80-degree threshold in some areas. Early season typhoons tend to form farther south, closer to the equator, where waters warm first. They're often weaker, struggling against atmospheric conditions that haven't fully aligned yet. Wind shear remains high. The atmosphere hasn't settled into its summer pattern. Many early season disturbances fail to organize. By August, everything changes. 6 months of intense tropical sunlight have heated vast expanses of ocean. The warm water depth has increased to 200 feet or more in many areas. The jet stream has retreated northward, reducing wind shear across typhoon formation regions. High-pressure systems have positioned themselves in ways that promote storm development. Nature's pieces have fallen into place. September represents the absolute peak. Statistically, more typhoons form in September than any other month. Ocean temperatures reach their annual maximum. The atmosphere achieves its most favorable configuration. This is when multiple storms can exist simultaneously across the Pacific, each one tracking along slightly different paths determined by steering currents. October maintains high activity, but subtle changes begin. The sun's angle decreases as the northern hemisphere tilts away from summer. Ocean temperatures start their gradual decline, though they remain above 80 degrees in most of the typhoon basin. The jet stream begins its seasonal migration back toward the equator, increasing wind shear in the northern reaches of the formation zone. By November and December, typhoon activity drops noticeably. Ocean temperatures fall below 80 degrees in the northern areas. Formation shifts southward again, back toward the equator, where waters stay warmest longest. Late season typhoons often track differently than peak season storms because steering currents have changed with the seasons. January through April represents the quiet period, though not completely inactive. The Western Pacific can produce typhoons any month of the year because some areas near the equator maintain water temperatures above 80 degrees permanently. These off-season storms are rare, perhaps 1 or 2 per year, but they prove that given sufficient warmth, typhoons need no calendar. This seasonal pulse occurs in every tropical cyclone basin worldwide, though timing varies by hemisphere. The Atlantic hurricane season peaks in September, just like the Pacific typhoon season. The Southern Hemisphere cyclone season peaks in February and March, when summer occurs below the equator. The pattern repeats, hemisphere by hemisphere, driven entirely by solar heating. Understanding this rhythm provides comfort through predictability. Communities in typhoon-prone regions know when to heighten vigilance. Ship captains plan routes around peak season. Insurance companies adjust coverage. Agriculture times plantings to avoid peak months. The predictability allows adaptation. It also means typhoons aren't ambushes. They announce themselves through seasonal patterns refined over millions of years. Nature doesn't hide its intentions. The warming ocean telegraphs increased risk. The cooling ocean signals safety's return. We have months of warning built into the planetary cycle itself, as reliable as sunrise. These seasons bring storms with surprisingly gentle names. Typhoons have names like Maria, Haiyan, Mangkhut, and Nepartak. These aren't random choices or dramatic labels invented by journalists. They're part of a carefully organized system maintained by the World Meteorological Organization, designed to make tracking storms easier and communication clearer. Before the naming system existed, storms were identified by their coordinates, latitude and longitude numbers. This created confusion when multiple storms threatened at once. Imagine a weather bulletin saying, "The storm at 15 degrees north, 135 degrees east is intensifying, while the system at 18 degrees north, 140 degrees east is weakening." People mixed them up constantly. Mistakes happened. Preparations failed. The solution emerged in the mid-20th century. Give each storm a short, distinctive name. Maria can't be confused with Jose. Haiyan sounds nothing like Mangkhut. A name creates identity, makes the storm memorable, and allows quick reference in conversations, broadcasts, and emergency communications. The system worked so well that all tropical cyclone basins worldwide adopted it. The Western Pacific uses a unique approach. Unlike the Atlantic, which cycles through alphabetical lists of names, the Pacific draws from a pool of 140 names contributed by 14 different countries and territories in the region. Each country submitted 10 names reflecting their language and culture. Japan contributed Usagi, meaning rabbit. China added Longwang, meaning Dragon King. The Philippines added Tujuan. Thailand contributed Nul. These names cycle through in predetermined order. When a storm forms, it receives the next name on the list. After all 140 names are used, the list starts over from the beginning. This takes about 3 to 4 years, depending on how active the season is. Some years produce 30 typhoons. Other years, maybe 20. The names keep cycling regardless. Certain names get retired permanently, removed from the list, when a storm causes exceptional destruction or death. The Philippines requested retirement of Haiyan after the 2013 typhoon killed over 6,000 people. Japan retired Takage after it caused severe damage in 2004. These retired names become historical markers, permanent reminders of particular events. New names replace them in the rotation. The naming system serves another subtle purpose. It humanizes these natural phenomena. A name makes the storm feel less like an impersonal force and more like something we can discuss, track, and prepare for. Studies have shown that named storms receive better media coverage and prompt more serious preparation than unnamed weather systems. The name demands attention. There's no correlation between names and intensity. A gentle name like butterfly can become a Category 5 monster. A fierce name like dragon can fizzle into a weak tropical storm. The name is assigned at formation, when the storm is still just a tropical storm, before anyone knows how strong it will become. This removes any unintentional bias in naming. Meteorologists around the world now use these names in official forecasts, research papers, and historical records. When scientists discuss the 2013 Pacific typhoon season, they can simply say Haiyan, and everyone knows exactly which storm they mean. The name becomes shorthand for complex data about track, intensity, and impact. These names have documented some of history's most remarkable storms, including ones that traveled incredible distances. Some typhoons defy expectations, lasting far longer and traveling much farther than typical storms. These outliers reveal the upper limits of what tropical cyclones can achieve when conditions align perfectly. Their stories aren't tales of destruction, but of endurance, nature's marathon runners that refuse to quit. Typhoon John holds the record for longevity. It formed in August 1994 and lasted 31 days, from August 11th to September 10th. During that month, it traveled over 8,000 miles across the Pacific Ocean. Even more remarkably, it crossed the international dateline twice, technically becoming a hurricane, then a typhoon again, then a hurricane once more, as it zigzagged between ocean basins. John's persistence came from staying over warm water almost its entire life, constantly refueling. The storm weakened and strengthened multiple times during its journey. It reached Category 5 intensity, with winds of 175 miles per hour at its peak. Then, it would weaken to Category 1 or even tropical storm status when conditions turned unfavorable. But it never completely dissipated. Every time it seemed ready to die, it would find another patch of warm water or a favorable atmospheric setup and regenerate. Typhoon Nancy, which struck in 1961, holds a different kind of record. It produced the strongest winds ever recorded in a tropical cyclone, with sustained speeds estimated at 215 miles per hour. Modern analysis suggests this measurement might have been slightly overstated due to different measurement techniques used in that era. But even conservative estimates place Nancy's winds above 185 miles per hour. The storm maintained Category 5 intensity for 3 consecutive days. What makes Nancy's intensity remarkable is that it occurred in an era before satellite monitoring. Ships and island stations measured it using instruments that couldn't capture the full picture. If Nancy formed today, satellites would document every detail of its structure. In 1961, much of its power went unobserved over open ocean, known only through post-storm analysis. Typhoon Tip, which formed in October 1979, earned its place in history through sheer size. It remains the largest tropical cyclone ever recorded, with tropical storm force winds extending 1,580 miles in diameter. You could fit 2 United States side by side within Tip's wind field. Despite this enormous size, Tip also achieved Category 5 intensity, proving that a storm can be both massive and powerful simultaneously. Tip's central pressure dropped to 870 millibars, the lowest pressure ever recorded in any tropical cyclone worldwide. This broke the previous record and still stands today. That pressure reading represents an almost perfect vacuum at sea level, a testament to how efficiently Tip's circulation had organized itself. Lower pressure wasn't possible while maintaining the structural integrity required for a tropical cyclone. These record holders share common traits. They all formed during periods of optimal atmospheric conditions. They stayed over exceptionally warm water. They avoided land for extended periods, allowing uninterrupted development. And they benefited from low wind shear, which prevented their circulation from being torn apart. These weren't lucky flukes. They were storms that found ideal conditions and maximized their potential within physical constraints. Their existence proves that typhoons have predictable upper limits. They can't grow infinitely large or infinitely strong. Physics constrains them, but within those constraints, they can achieve remarkable feats of atmospheric engineering that deserve recognition not as monsters, but as natural wonders. These long journeys follow invisible highways in the sky. Typhoons don't wander randomly across the ocean. They follow invisible highways called steering currents, rivers of air in the upper atmosphere that guide storms along predictable paths. Understanding these currents transforms typhoon movement from mysterious to mathematical, from chaotic to choreographed. The subtropical ridge plays the primary role. This semi-permanent high-pressure system sits north of the tropical formation zone in the Pacific. High-pressure systems rotate clockwise in the northern hemisphere, and this rotation creates easterly winds along their southern edge. Newly formed typhoons get caught in these easterly winds and travel westward toward Asia. Think of the subtropical ridge as a guardrail on a highway. It doesn't push the typhoon directly, but channels it along a particular path. As long as the typhoon remains south of the ridge, it continues moving west. The typical track carries storms from the open Pacific toward the Philippines, Taiwan, or southern Japan. This path repeats so consistently that meteorologists can predict likely trajectories days in advance just by knowing where the ridge is positioned. But the ridge shifts with the seasons. In summer, it extends farther north. In autumn, it retreats southward. These shifts alter typhoon tracks. Early season storms often recurve, turning northward and eventually northeastward as they reach the western edge of the ridge. Late season storms tend to maintain westward tracks longer, sometimes making landfall in Vietnam or southern China, rather than recurving out to sea. The jet stream adds another layer of guidance. This fast-moving river of air at high altitudes, typically around 30,000 feet, flows from west to east across the mid-latitudes. When a typhoon approaches the jet stream, it can get captured and accelerated eastward. This process, called extratropical transition, changes the storm's characteristics, but can carry it across entire ocean basins in just days. Wind shear, the change in wind speed or direction with height, also steers storms. Strong shear can push the upper levels of a typhoon in one direction, while lower levels move another direction, creating a tilt. This tilt often indicates the storm is being steered by competing atmospheric forces. Storms fighting against shear usually weaken, but sometimes they manage to realign and intensify once conditions improve. Meteorologists track steering currents using weather balloons, satellite data, and computer models. They identify high-pressure systems, measure wind speeds at various altitudes, and calculate the resultant force on the storm. These calculations explain why some typhoons make sharp turns, while others maintain steady courses. Every turn, every acceleration, every deceleration connects to identifiable atmospheric features. Occasionally, steering currents collapse. A typhoon finds itself between competing systems with no clear dominant flow. When this happens, the storm stalls, drifting slowly or even looping in circles. Stalled typhoons can be particularly damaging because they dump enormous amounts of rain over the same area for days. But even stalling follows atmospheric logic, the absence of steering rather than random behavior. The predictability of these patterns allows forecast accuracy to improve year after year. Modern 5-day track forecasts are as accurate as 3-day forecasts were just 2 decades ago. Understanding steering currents transformed typhoon prediction from educated guessing to science. But something can stop even the mightiest typhoon. The moment a typhoon crosses from ocean to land, its death sentence begins. Not instant collapse, but gradual starvation. Cut off from the warm ocean water that fuels it, the storm starts consuming itself, burning through its remaining energy reserves with nothing to replenish them. Friction provides the first blow. Ocean surfaces are smooth, offering little resistance to wind. Land surfaces are rough with trees, buildings, hills, and varied terrain. This friction slows the wind at ground level, while upper-level winds continue at full speed. The mismatch disrupts the storm's carefully organized circulation. Energy that was driving rotation now converts to turbulence. The eye wall begins to break apart. Mountains accelerate this destruction. When typhoons encounter mountain ranges, the forced uplift creates intense rainfall on the windward slopes as moist air rises and cools. But this also drains moisture from the system faster than evaporation can replace it. Mountain ranges like those in Taiwan or the Philippines can reduce a Category 4 typhoon to tropical storm strength within hours. The storm essentially crashes into a wall it cannot flow around efficiently. The fuel cutoff matters most. Over land, evaporation drops dramatically. Soil and vegetation hold moisture differently than open ocean. Even if it's raining heavily, that water isn't returning to the atmosphere fast enough to sustain the storm. The latent heat engine sputters. Without constant energy input, the low pressure center begins filling in. As pressure rises at the center, the pressure gradient weakens, and with it, the winds decrease. Temperature differences also equalize. The warm core structure that defines a typhoon requires continuous heating from below through evaporation and latent heat release. Over land, surface temperatures actually cool during a typhoon due to cloud cover and rain. The temperature difference between the core and surroundings shrinks. This reduces buoyancy, weakening the updrafts that maintain the storm's vertical structure. The process takes time. A strong Category 4 typhoon doesn't become a tropical depression immediately upon landfall. The first 12 hours might see reduction to Category 2 or 3. The next 12 hours might bring tropical storm status. After 24 to 36 hours over land, most typhoons have weakened to tropical depressions or dissipated entirely. The exact timeline depends on storm size, intensity at landfall, and terrain features. Large typhoons survive longer over land than small ones. Their greater mass carries more momentum. They contain more moisture in their vast cloud systems. This allows them to maintain tropical characteristics further inland. Some large typhoons have remained tropical storms 200 miles inland, far beyond what smaller storms could achieve. Rain becomes the primary concern during this weakening phase. As the winds die down, the threat shifts. A weakening typhoon can still drop 20 to 40 inches of rain over mountainous terrain. This causes flooding and landslides that often produce more casualties than the wind ever did. The dying storm releases all its remaining moisture at once, unable to hold it aloft as circulation fails. Eventually, the typhoon loses its tropical characteristics completely. It becomes a remnant low, just a swirl of clouds and light rain. The energy dissipates into the atmosphere, redistributing heat and moisture across continents. What was once a Category 5 monster becomes a weak weather system that barely registers on satellite imagery. Yet even in weakening, they serve an important purpose. Typhoons aren't just destructive forces. They're essential components of Earth's climate system, performing jobs that no other weather phenomenon can accomplish as efficiently. They transport heat, deliver water, and maintain balance across vast stretches of our planet. The heat transport function is crucial. Tropical oceans absorb enormous amounts of solar energy. Without a mechanism to move this heat toward the poles, the tropics would continue heating while high latitudes froze. Typhoons act as heat pumps, pulling warm air and water vapor from the tropics and carrying it poleward. When they recurve northward, they inject tropical warmth into mid-latitude regions, moderating temperatures. A single typhoon can transport as much heat energy as several months of normal atmospheric circulation. This redistribution prevents the tropical Pacific from becoming dangerously hot while providing warmth to regions that would otherwise be colder. The energy doesn't disappear. It spreads out, evening temperature gradients across the hemisphere. Water delivery matters even more for many regions. Taiwan receives about 30 to 40% of its annual rainfall from typhoons. Parts of Japan depend on typhoon season for similar proportions. The Philippines, despite the destruction typhoons can cause, relies on them for agricultural water supplies. These aren't optional storms that people could do without. They're scheduled deliveries that entire ecosystems anticipate. The rainfall isn't gentle. A typhoon might drop 20 inches in 24 hours, causing floods. But that water percolates into the soil, refills reservoirs, and recharges aquifers, that sustain millions during dry months. In some regions, the absence of typhoons creates drought conditions worse than the flooding their presence causes. The violence of delivery doesn't negate the necessity of what's being delivered. Agricultural systems in typhoon-prone regions have adapted to this reality. Farmers plant certain crops knowing typhoons will arrive. They construct terraced fields that can handle extreme rainfall. They time harvests around typical typhoon season. These aren't desperate adaptations to an avoidable threat, but practical responses to a reliable climate pattern that brings both risk and benefit. Typhoons also ventilate the atmosphere, mixing air masses that might otherwise stagnate. They bring fresh marine air deep into continental interiors. They redistribute moisture vertically through the atmosphere, affecting cloud formation patterns for weeks after they dissipate. This mixing influences weather patterns across entire regions, extending the typhoon's impact far beyond its physical track. The ocean benefits too. Typhoon winds mix surface water with deeper water, bringing nutrients from below to sunlit surface layers. This nutrient upwelling triggers phytoplankton blooms that feed entire marine food webs. Fisheries often see productivity increases in the weeks following typhoon passage. The storm's churning creates fertility in the water column. Some scientists study whether typhoons influence monsoon patterns. The heat and moisture they inject into the atmosphere may strengthen or prolong monsoon systems that deliver rain to billions of people across Asia. The connections are complex, still being researched, but evidence suggests typhoons play roles in climate patterns that extend far beyond their immediate impact zones. Viewing typhoons solely as disasters misses their function. They're part of how Earth maintains habitable conditions. They prevent overheating in the tropics. They deliver water to regions that depend on it. They redistribute energy that would otherwise create more extreme temperature contrasts. They're not malfunctions in the climate system. They are the climate system working as designed. This role reveals something surprising about climate balance. Typhoons cool the oceans they travel across. This might seem counterintuitive, since warm water fuels them, but the cooling effect is real, measurable, and surprisingly important for Earth's climate balance. These storms prevent tropical oceans from overheating, acting as natural thermostats. The primary cooling mechanism is mixing. Typhoon winds don't just blow across the ocean surface. They penetrate into the water, creating waves and currents that churn the upper layer. This mixing brings cold water from depths of 300 to 600 feet up to the surface. That deep water, shielded from sunlight for months, can be 10 to 15 degrees Fahrenheit cooler than surface water. When it reaches the surface, it absorbs heat from the atmosphere and sunlight, cooling the area the typhoon just passed through. Satellite measurements show this cooling clearly. Behind a typhoon's track, sea surface temperatures can drop 4 to 9 degrees Fahrenheit. The cooling extends along the entire path, sometimes hundreds of miles long and 50 to 100 miles wide. This cooler wake persists for weeks, slowly warming back to ambient temperatures as the sun reheats the surface layer. Evaporation provides additional cooling. Strong typhoon winds dramatically increase evaporation rates across the ocean surface. Evaporation removes heat from water, the same principle that makes sweating cool your skin. The faster the wind, the more evaporation, the more cooling. Peak evaporation occurs in the eye wall, where winds reach maximum speeds. This evaporative cooling can remove heat equivalent to the energy output of thousands of power plants spread across the storm's circulation. The water vapor carries this heat into the atmosphere, where it eventually radiates to space. The ocean loses thermal energy. The global heat budget stays balanced. Some climate scientists suggest typhoons may help regulate planetary temperatures by preventing heat buildup in tropical oceans. Without tropical cyclones, the Pacific and Atlantic would continue absorbing solar energy throughout summer with no efficient release mechanism. Temperatures could rise several degrees higher than currently observed. This extra heat would affect global circulation patterns, potentially creating more extreme weather elsewhere. The cooling also creates a negative feedback loop for the typhoon itself. As it cools the water beneath it, the storm reduces its own fuel supply. This self-limiting mechanism prevents typhoons from growing indefinitely. They create the conditions that eventually weaken them. It's a natural governor, a built-in constraint that maintains balance. Researchers measure ocean heat content before and after typhoon seasons. The total heat stored in the upper ocean decreases by measurable amounts. This heat doesn't disappear from Earth's system entirely, but it redistributes from concentrated ocean storage into the broader atmosphere, where it can radiate to space more efficiently. Typhoons accelerate heat loss from the planet. The mixing also affects ocean circulation on longer timescales. Bringing cold water to the surface changes density structures in the upper ocean. These density changes influence currents that persist long after the typhoon dissipates. Some oceanographers study whether typhoon activity affects major current systems, like the Kuroshio current that flows along Japan's coast. Understanding this cooling function changes how we view typhoons. They're not just weather events, but active participants in Earth's temperature regulation. They take excess heat from where it accumulates and redistribute it through mixing and evaporation. The violence of their winds serves a purpose beyond destruction. It serves planetary cooling. Ancient observers noticed patterns in these storms. Long before satellites and computer models, people living in typhoon zones developed sophisticated methods for predicting these storms. These weren't superstitions, but careful observations accumulated over generations, tested against reality season after season. Modern science validates much of this traditional knowledge. Polynesian navigators read ocean swells with remarkable accuracy. Swells are long wavelength waves that travel thousands of miles from their origin. A typhoon generates distinctive swell patterns that arrive days before the storm itself. Experienced navigators could feel these swells through the hull of their canoes, identifying the telltale rhythm that indicated distant storm activity. They knew which swell patterns meant safety and which meant seeking shelter. The technique required understanding that different storms create different swell periods. A weak tropical storm generates choppy, irregular swells. A powerful typhoon produces long, regular swells spaced 15 to 20 seconds apart. By timing the interval between swells and noting their direction, navigators could estimate storm location and intensity, sometimes pinpointing it within 100 miles. Chinese farmers developed elaborate systems based on cloud observation. Certain cloud formations reliably preceded typhoons by 24 to 48 hours. cirrus clouds streaming from a single point on the horizon indicated outflow from a distant storm. Lower-level clouds moving in opposite directions suggested the complex wind patterns near a typhoon's periphery. Red sunrises caused by high-altitude ice crystals often preceded typhoon arrival by a day. These observations were codified into agricultural calendars and weather proverbs passed down through families. They specified which crops to harvest early if certain signs appeared. They indicated when to secure boats and reinforce structures. The knowledge was practical, tested annually, refined through success and failure. Japanese coastal communities watched animal behavior. Certain fish species moved to deeper water 12 to 24 hours before typhoons arrived, responding to pressure changes humans couldn't detect without instruments. Birds stopped singing and sought shelter. Even insects changed their patterns, reducing activity as pressure dropped. These behavioral changes provided warning times sufficient for preparation. The pressure changes these animals detected were subtle, perhaps 2 to 3 millibars below normal. Human nervous systems don't register such small variations consciously, though some people reported headaches or joint pain before storms. But animals, with nervous systems tuned to different sensitivities, reacted consistently enough that communities learned to trust these signs. Filipino typhoon prediction integrated multiple signals. Elders watched for halo rings around the moon, caused by ice crystals in the high clouds that precede typhoons. They noted wind direction changes, particularly when the steady trade winds shifted to come from unusual directions. They observed ocean color changes as upwelling and current shifts occurred. Each sign alone meant little. Combined, they built confidence in predictions. The accuracy wasn't perfect. These methods could predict typhoon arrival within a day or two and provide rough estimates of intensity. They couldn't forecast exact landfall locations or predict sudden intensification. But for communities without modern technology, this knowledge meant the difference between preparation and surprise. Modern meteorology hasn't made this traditional knowledge obsolete. It's enhanced it. Scientists now understand the physical mechanisms behind observations that worked empirically for centuries. Cloud patterns indicate upper-level wind flows. Ocean swells reveal distant storm energy. Pressure changes explain animal behavior. The wisdom was real. The observations were sound. Only the explanations were incomplete. Today's technology sees what ancient observers could only imagine. Weather satellites orbit Earth every 90 minutes, passing over the same locations multiple times daily. This constant surveillance transformed typhoon forecasting from educated guessing to precision tracking. Nothing about these storms hides anymore. Every rotation, every strengthening pulse, every subtle change gets recorded and analyzed. Geostationary satellites hover 22,000 miles above the equator, moving at exactly the same speed as Earth's rotation. From their fixed position, they watch the same patch of ocean continuously, capturing images every 10 minutes. When a typhoon forms, these satellites document its entire life from birth to death. Meteorologists can scroll through a day's images like frames in a film, watching the storm evolve in fast motion. The visible light cameras show cloud structure with stunning clarity. The spiral bands, the eye formation, the symmetry of organization, all become visible from space. Meteorologists assess storm health by examining these structures. A symmetric storm with tightly wound spiral bands and a clear eye is healthy and likely intensifying. An asymmetric storm with ragged features is struggling and probably weakening. Infrared sensors measure temperature. Cold cloud tops indicate strong updrafts that have pushed clouds to extreme altitudes where temperatures drop to -80 degrees Fahrenheit or colder. The coldest clouds show up as bright white on enhanced infrared imagery. A large area of these cold clouds surrounding the eye suggests a powerful storm with intense convection. Warming cloud tops indicate weakening. Microwave sensors penetrate through the clouds themselves, revealing structure invisible to optical cameras. These sensors detect the liquid and ice water inside clouds, mapping rainfall rates across the entire storm. They identify the eye wall location precisely, even when obscured by upper-level clouds. They measure how efficiently the storm is converting moisture into energy. Specialized satellites carry scatterometers that measure surface wind speeds by analyzing how ocean waves scatter radar signals. Different wind speeds create different wave patterns that reflect radar in characteristic ways. These measurements provide wind data across the entire storm, not just at a single point. Forecasters can see exactly how large the wind field has become. All this data flows into forecast centers within minutes of collection. Meteorologists combine observations from multiple satellites, creating three-dimensional pictures of storm structure. They track eye diameter changes to the mile. They measure how quickly the central pressure is falling. They note whether rain bands are becoming more organized or fragmenting. The result is unprecedented forecast accuracy. Modern 3-day track forecasts hit within 100 miles of actual landfall about 90% of the time. 5-day forecasts, which were impossible to issue with any confidence just 30 years ago, now provide useful guidance. Communities have days to prepare instead of hours. Satellites don't prevent typhoons. They can't weaken them or steer them away from populated areas. What they do is eliminate surprise. Every typhoon that forms gets detected within hours. Every movement gets tracked. Every intensity change gets documented. This transformation from unknown threat to monitored phenomenon represents one of meteorology's greatest achievements. The constant watch means that today, when a typhoon threatens, it does so with full advance notice. The storm announces itself through satellite imagery that updates faster than hourly. People can watch the same images meteorologists analyze, seeing for themselves what approaches. But one question remains difficult to answer. Meteorologists can tell you where a typhoon will be in 5 days with impressive accuracy. But ask them how strong it will be, and confidence drops dramatically. Intensity forecasting remains one of meteorology's most stubborn challenges, not because scientists lack tools, but because the processes controlling intensity happen at scales too small for current models to capture perfectly. Track forecasting succeeded because steering currents operate at large scales. High-pressure systems, jet streams, and wind patterns extend across thousands of miles. Computer models handle these features well. Feed them today's atmospheric state, and they accurately simulate how these large-scale features will evolve. A typhoon caught in those currents follows a predictable path. Intensity depends on smaller scale processes. Whether a typhoon strengthens or weakens can hinge on factors operating over just a few miles. An inner eye wall can replace an outer eye wall in a process that completely reorganizes the storm's core. This eye wall replacement cycle temporarily weakens the typhoon before it re-strengthens, sometimes to greater intensity than before. The cycle takes 12 to 36 hours and dramatically affects intensity, yet it happens across a space of just 40 miles. Ocean temperatures matter at fine scales too. A typhoon passing over a patch of slightly cooler water might weaken. But if that patch is only 30 miles across, the storm could traverse it in a few hours and re-intensify on the other side. Whether this happens depends on the exact alignment of storm track and ocean features. A shift of just 10 miles can mean the difference between weakening and maintaining strength. Wind shear affects intensity but changes rapidly. A typhoon in an environment with 5 knots of wind shear will intensify. Increase shear to 20 knots and intensification stops. The storm might even weaken. But shear values can change in just 6 hours as upper-level winds shift. Forecasting these shear changes days in advance remains difficult because they depend on atmospheric waves and disturbances that models struggle to predict precisely. Dry air intrusions cause sudden weakening when they penetrate the storm's core. Moist tropical air fuels typhoons. Dry air from mid-latitudes chokes them. Whether dry air reaches the center depends on exactly how it's positioned relative to the storm and how vigorously the storm circulation keeps it at bay. These interactions happen over distances of 50 to 100 miles, requiring model resolution finer than currently available for routine forecasting. The atmosphere's natural chaotic behavior amplifies small uncertainties. 2 nearly identical initial conditions can produce different intensity forecasts within 48 hours. Meteorologists call this sensitive dependence on initial conditions. In intensity forecasting, it means that tiny errors in measuring today's atmospheric state lead to significant forecast differences for tomorrow's storm strength. Forecasters use ensemble techniques, running models, multiple times with slightly different initial conditions to see the range of possible outcomes. If all ensemble members show intensification, confidence is high. If half show strengthening and half show weakening, confidence drops. The spread between ensemble members reveals forecast uncertainty. Despite these challenges, intensity forecasting improves gradually. Better satellites provide more detailed observations. Higher resolution models capture smaller scale processes. Improved understanding of eye wall cycles, ocean coupling, and shear effects refines predictions. Today's 24-hour intensity forecasts match the accuracy of 12-hour forecasts from 2 decades ago. The humility in acknowledging these limitations is actually wisdom. Nature operates at scales. We're still learning to observe and model. Admitting uncertainty is more honest than false confidence. Despite these challenges, patterns emerge over time. The question everyone asks is whether typhoons are changing. Are they becoming stronger, more frequent, following different paths? The answer is complex, revealing itself gradually through decades of data and careful analysis. climate science suggests changes are occurring, though not always in the ways people expect. Ocean temperatures have risen about 1.5 degrees Fahrenheit globally since the late 1800s. In tropical regions where typhoons form, the increase is similar. This warming expands the area where sea surface temperatures exceed the 80-degree threshold needed for formation. Waters that used to stay too cool now warm enough to support typhoons. The potential formation zone has grown, particularly at higher latitudes. But warmer oceans don't automatically mean more typhoons. Formation requires specific atmospheric conditions beyond just warm water. Wind shear must be low. The atmosphere must be moist at multiple levels. Upper-level divergence must support outflow. These conditions don't necessarily become more common as temperatures rise. In fact, some climate models suggest that total typhoon numbers might decrease globally, even as temperatures warm. What appears more certain is that intense typhoons may become more common. The relationship between ocean heat and maximum potential intensity is well established. Warmer water can support stronger maximum winds before the storm reaches its physical limits. This doesn't mean every typhoon strengthens more. It means the ceiling on possible intensity rises. Category 5 storms might become slightly more frequent, while overall storm numbers stay the same or even decline. Rainfall rates show clearer trends. Warmer air holds more moisture. At typical typhoon temperatures, each degree Fahrenheit of warming allows the atmosphere to hold about 4% more water vapor. This extra moisture doesn't disappear. It falls as rain. Climate models consistently project that typhoon rainfall rates will increase even if wind speeds don't change dramatically. The same storm in a warmer climate drops more rain. Some research suggests typhoon tracks might shift. As the tropical belt expands with warming, the latitude where typhoons typically form could shift poleward. This would alter which regions face the greatest risk. Areas currently on the northern edge of typhoon territory might see increased activity. Regions in the heart of the current zone might see slight decreases. These shifts would unfold over decades, not years. The speed at which typhoons move could also change. Some studies indicate storms are moving more slowly than they did 50 years ago. Slower movement means more rain over the same location, increasing flood risk. The mechanism isn't fully understood, but might relate to changes in atmospheric circulation patterns that steer storms. Uncertainty remains high for many of these projections. Typhoons are complex systems influenced by multiple factors that interact in ways not fully captured by current models. Scientists present findings with appropriate caveats, distinguishing between high-confidence results, like increased rainfall, and lower confidence projections like track changes. What's clear is that coastal communities should plan for a future where typhoon risks evolve. Building codes, evacuation plans, and infrastructure must account for potentially stronger maximum intensity storms, heavier rainfall, and possible track shifts. Adaptation requires accepting that the climate system isn't static, that patterns established over past centuries may not hold for future decades. This uncertainty shouldn't paralyze action. It should motivate continued research, improved forecasting, and thoughtful preparation for a range of possible futures. Understanding the possibilities, even without perfect prediction, allows wiser choices than ignoring potential changes altogether. In understanding these storms, we find something unexpected. Typhoons remind us that nature operates at scales beyond human control, but within human understanding. Their power isn't malicious. It has no intent, no anger, no desire to harm. It's mechanical, following laws of physics as reliable and predictable as the sunrise. By studying them, we transform fear into knowledge, helplessness into preparation, and apparent chaos into recognizable pattern. The spiral structure that seems so menacing from satellite images is just air following the path of least resistance on a rotating sphere. The destructive winds are simply pressure gradients equalizing through motion. The torrential rains are water vapor condensing back to liquid, releasing energy it absorbed days earlier. Every aspect that appears threatening has a physical explanation, a cause that can be understood and predicted. This understanding brings unexpected peace. Typhoons aren't random catastrophes that strike without warning. They announce themselves through rising ocean temperatures, through organized cloud patterns, through pressure drops that satellites measure from space. They follow steering currents meteorologists can track. They intensify and weaken according to environmental conditions we can monitor. Even their seasonal rhythm follows Earth's tilt and solar heating with clockwork regularity. The violence, when it comes, serves purposes we rarely consider in the moment. Heat transport from equator toward poles, water delivery to regions that depend on it, ocean mixing that brings nutrients to the surface, atmospheric ventilation that prevents stagnation. These functions don't erase the damage typhoons cause, but they reveal that these storms are integrated parts of Earth's climate system, not malfunctions or mistakes. Ancient observers knew this intuitively. They watched cloud patterns and ocean swells. They noted animal behaviors and pressure changes. They built their knowledge through generations of careful observation, learning to read nature's signals. Modern science didn't replace this wisdom. It explained it, providing the physical mechanisms behind observations that worked empirically for centuries. Today's satellites and computer models extend our vision beyond what any individual could observe in a lifetime. We see storms forming 3,000 miles away. We track every movement. We measure intensity changes hour by hour. The technology doesn't prevent typhoons, but it eliminates the fear that comes from ignorance. What we understand, we can prepare for. What we can measure, we can predict. As you settle into rest tonight, let the image of a typhoon spiral calm your mind. That spiral follows mathematical rules. The eye at its center demonstrates how extremes can coexist. Violence surrounding perfect stillness. The predictable season shows nature's rhythm. The gradual weakening over land reveals self-limiting processes. Even in nature's greatest displays of atmospheric energy, there is order. Even in the storm, there is structure. Even in change, there are laws. The universe operates on principles we can discover, measure, and understand. This knowledge is power, not over nature, but over the fear that comes from not understanding it. If you found peace in tonight's story, show us some love by hitting that like button and subscribing to the channel. tomorrow night, we'll explore another corner of our amazing universe together. What mysteries would you like us to uncover next? Let us know in the comments. Sleep well, knowing that understanding brings peace. And nature's patterns, however powerful, are knowable, predictable, and in their own way, beautiful.